Okay, so finally we're going to look at the theorem for the full Fourier series from minus L to L. So here we have f. F is defined on minus L to L. So f is a function defined on minus L to L. The full Fourier series, f of x, is given by 1/2 a0 plus the sum, k equals 1 to infinity, cosine k pi over L x plus bk sine k pi over L x. With similar formulas for the coefficients as we've already seen, ak is going to be equal to 1 over L, not 2 over L. It's going to be 1 over L times the integral from 0 to L f of y cosine k pi over L y dy, and bk is equal to 1 over L times integral from 0 to L f of y sine k pi over L y dy. There we have it. I now see this marker, so it's hard for me to tell if it's the marker that's going bad or the board. Okay, so now we're going to look at the theorem regarding convergence of series for the full trigonometric series, the full cosine and sine series. Full meaning we have both cosine and sine functions. Okay, and it's going to be pretty simple. So this is going to be the FFS, so full Fourier series. 1, find the periodic extension. Okay, so now the function is defined from minus L to L, so the even and odd stuff we don't care so much about. And 2, the full Fourier series will converge to the periodic extension where continuous, so PE means periodic extension, where continuous, and otherwise to the average at a jump. Okay, so one sort of hidden assumption here is that our functions that we're going to be looking at are going to be bounded from 0 to L. In particular, they're going to be piecewise continuous on 0 to L. Okay, so the only type of discontinuity we're going to have is a jump discontinuity. And just then when I said 0 to L, I also meant minus L to L. All right, so let's look at an example. So let's say I have a function going from minus 1 to 1. And let's say it's going to look something roughly like this. Make it even more complicated for me to try to figure out how to draw something like this. We'll say this is 2 and this is 1. Okay, so now I just want to sketch the periodic extension of this. So let's say this is 2, this is 3, this is minus 2, this is minus 3. So I'm going to sketch the periodic extension. I'm just going to take this and copy and paste it. It should be like that and like that. So okay, periodic extension is going to take it and copy and paste it. Okay, if I look from 1 to 3, I'm going to do that in purple. If I look from 1 to 3, I'm going to start here from 1 to 2 and go up like this. And I didn't show it, but right here, it's open there. And then we're going to have something like this. Okay, and there's no ambiguity. Where's the ambiguity? Sorry, my markers are not. This is like that. This is filled in. Okay, so where is there ambiguity in the extension? Well, there's going to be an ambiguity right here because, again, we have, or no, sorry. Yes, there's an, apologies. There's an ambiguity right here because I look at this part, I know it's defined there, but this part is defined there. So we're going to have an ambiguity here that I'm going to denote with an open thing like that. Okay, and then if I look from -3 to 2, again we'll have the ambiguity here, like this. And when I say ambiguity, I just mean the extension is not well defined there because there's two competing things that it could be equal to. Okay, so this is the periodic extension. Okay, this isn't the full Fourier series yet of the function. This is just the periodic extension. And now I want to, by filling in these holes, so wherever there's not a hole, I know the function is going to, the only place where they could possibly not converge is going to be at these jump discontinuities, Everywhere else, the Fourier, full Fourier series is going to converge there where the function is continuous. Okay, so now let me look at the jump discontinuities. So if I look at this jump discontinuity, what are the values? Well, I've got 1 here. The left-hand limit is 1. The right-hand limit is 0. So the average is 1/2. So it's going to converge to halfway between there. So something like that. Okay, what about here? Well, here the limit is 2. Here the limit is 0. The average value, sorry, this is -2. -2 plus 0 is -2. Divided by 2 is 1/2. And so it will converge to -1/2 there. Okay, similarly, it will converge to 1/2 here. So this is 1/2. This is -1. It'll converge to -1 here, and it will converge to 1/2 there. Okay, so in particular, if I just want to know what's happening from -1 to 1, notice where it's converging from -1 to 1. If I just look at -1 to 1, it's converging to 1/2 here. -1 here, 1/2 here, and -1 there. Okay, and again, the reason it's not converging to 0 is because we have cosine and sine terms. All right, and so how can we determine, so this is how we sketch the full Fourier series, and it also tells us what it converges to on the interval of interest, which in this case is -1 to 1, or more generally might be -L to L. Okay, in the next video, we're going to look at some stuff about orthogonality and remind ourselves about why we care about sine and cosine functions to begin with.